Hi, here we are discussing about the project AdAM, Adaptive Approximate Multiplier for Fault Tolerance in DNN Accelerator. Here, the logarithmic multipliers are widely applied in digital signal processing, machine learning and cryptography and imaging because this reduces the multiplication into additions and shifting. Here, the recent approximate design such as the Adaptive Fault Tolerance Approximate Multiplier targeted a deep neural network accelerator by optimizing a fault tolerance with a leading one directions and Mantis truncations. While effective for DNN reliability, the adaptive fault-tolerant approximate multipliers introduce a deterministic approximations errors, relies on limited carry lookalike adders and triple adaptive adders, and mainly focused on ASIC implementations without extensive FPGA exploration. To overcome these restrictions, we propose a hybrid logarithmic multiplier that employs a variable truncated and a variable higher order shifting method with an adaptive parallel prefix adder. Okay, so a leading one detector is designed in this paper to generate both the positions and the logarithmic value directly and reducing redundant computations. The parallel shifter is remodified with the adaptive truncations which lower area and delayed, and in addition is performed by hybrid parallel prefix adders where Bohum is used for LSB and Gongstone is used for MSB significant bit. It's achieving a higher speed and balanced area compared to the traditional triple carry adder method. Here the truncated and higher order bit are variable parameters which enables flexible precision controls and more accurate error management across the various applications. A compact Bohum adders is also used to logarithmic value additions, while the anti-logarithmic unit reconstructor results adaptively with a log n shifting for accuracy and efficiency. The novelty of this design lies in integrating hybrid parallel prefix adders with a variable truncated and higher order shifting method, making it more reliable and versatile than the extensive approximate approaches such as adaptive fault tolerant applications multiplier. So this architecture is implemented in Verilog crystals and verified on modelisms and synthesized on Xilinx Vertex 5 FPGA. Now we can verify the paper. So this paper is fully designed for the adaptive approximate multiplier. So here the adaptive is mainly focused for addition technique of this paper. Okay, so here initially it will be started with the leading one detector. So this leading one detectors will predict the leading value of the bit and it will be generated the log value and the indexing value. Okay, so here in the architecture, okay, so here the figure 3 it will be showing the AdAM architecture of the approximate multiplier. Initially it will be loading the A value and B value to the leading one directions code. Okay, so here the leading one directions it will be predict only the log value of the multiplications. Okay, so this is the architecture of the leading one code, and we remodified this architectures of the leading one detection method with the indexing value and log value based architectures. Okay, so here in the previous architectures they taken only the log value. As per the log value they shifted the bits using a parallel shifter method. Okay, and here they will be used for parallel left shift method. Okay, after the shifting method the adaptive adder it will be designed. Okay, so in this adaptive adder it will come with more complications of the design. It will have more number of shifting operations and more number of conditions with the protected bits and truncated bits and padding 0 bits and Mantis bits. Okay, with the higher order bit occupations. So this adaptive adders it will be designed with a ripple carry adder and carry lookalike adder method, and this ripple carry adders and carry lookalike adder method is a basic one. It not well balanced for speed, area and power stability. Okay, a new hybrid adder technique we designed with a Bohum and Gongstone based architectures. It will be designed with for this proposed method. Okay, so here initially start with the A and B. Okay, and this multiplier is also designed with the 8-bit architectures. So here initially the leading one detector it will be generating the index value and also for the Ka log and Kb log value, and the Ka log and Kb log value it will be added with a Bohum adder. Okay, and finally it will be using for the logarithmic functions. Okay, and the indexing value it will be used for the truncated parallel left shift method. Okay, the previous architectures it will be designed for only the parallel left shift method, but here we used for the truncated parallel left shift method, and after this truncations we just add the value only. Okay, but in this previous architectures we left shifter method, and after that it will be truncated happen in the adaptive additions. Okay, so previously we truncated means we resolve number of partial products based shifting method in this addition part. Okay, and here for this addition technique we used a hybrid adaptive parallel prefix adder method which using a Bahung and Kongstone adder. It will be referred using this paper. Okay, so here the hybrid adder block diagrams available. So it will be designed with a Bahung method and Kongstone method, and this architecture is also it developed with the cascaded parallel prefix addition method. Okay, so this Kongstone adders and Bahung adders, it will be referred using this paper. So this is a Kongstone adders and this is a Bahung adder architecture. Okay, and finally we developed this proposed architectures here, and this addition part finally it will become with the anti-logarithmic, and we taken as a product output. Okay, so this architectures we developed for 8-bit one. Okay, and this is a variable one, so variable truncations and variable h value. Okay, higher order value. Okay, so why? Because so in the previous one it's a fixed one, so it's having a fixed truncations method. Okay, so if you are fixed the LSB 4-bit means it will be generating the output only in the LSB 4-bit only. Okay, but depends upon the higher indexing value, so this truncated parallel left shifting method, it's automatically shifting the value, so it will become with a more accurate, and it will become with a less number of error differences. Okay, so in this work we have developed this multiplier at 8-bit size and also for 16-bit size in Verilog HCL code. Okay, so this is the top model architecture of this code: approximate multipliers, leading one detections method for A and B, and truncated parallel shifters, and also for hybrid adder technique. Okay, and this code also developed with a hybrid adder 8-bit architectures with a cascaded Kongstone method and Bahung architecture. Okay, and this is a simulation for the 8-bit code addition method. Okay, so here this one is an accurate adder and this is for multiplications. Okay, so here clock reset A value, B value. So here for verifications we will given a B value is constant and A value it will be varied with the incrementations. Okay, so if you are given A value in the incrementations, it will be present with this type of phase angle. Okay, and this is a product output, you can verify that. Okay, and this is a error difference. Okay, and this is the original value. Okay, so this is a approximations will be get. Okay, and this is the error value. So here, and this multipliers it will be take only 81 LUT in a Xilinx synthesis report, and it will come occupied slices equal to 29 and IOB equal to 32. Okay, and synthesis report we can analyze that delay. Okay, it will be occupied only 9.165 nanoseconds. Okay, so this multiplier also designed within a 16-bit architectures. It will be take LUT in 320 and occupied slice equal to 146. Okay, and we can verify the RTL schematic for this project in 8-bit or 16-bit. So this is the RTL schematic. So leading one detections, Bahung method, anti-logarithmic, okay, and truncated parallel left shift method. Okay, and this work we have compared it the 8-bit and 16-bit architectures, and we have written abstract document. So base paper, improvement, and proposed title, proposed abstract. Okay, existing system, disadvantages, and proposed architecture explanations. Okay, so and finally we come up with the literature review and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.